So this is the RISC-V BoF. It is a discussion section. That's the entire slides I've got. I don't know if Palmer or Jim have any more slides.
No.
Okay. And it's really because RISC-V's taken off, and because it does more work on RISC-V than any other architecture. Sci-Fi just does RISC-V. It's the number of companies in the RISC-V Foundation is growing all the time. So this is an opportunity for the GCC community and the wider GNU tools community to bring forward any issues that may be of concern. Now, Palmer's role in Sci-Fi is largely to keep an overview of everything that's going on. So I'll hand over to Palmer, and he perhaps give you a rundown of where we are, and I'll act sort of more as a moderator, and one of us will run that round with a microphone to get people to talk into, so we record everything on the tape. Okay, over to you, Palmer.
Okay, makes sense. Yeah, so I guess, so I'm Palmer. I've been involved in RISC-V for a few years now. I started at Berkeley when the ISA kind of started, and then I came to Sci-Fi with much of the original Berkeley people. And I started out as kind of the only software guy, so I ended up on maintaining sort of everything, and now kind of run the team that does all the RISC-V software stuff. So Jim's on the team. He's our GCC and Binutils guy and does a bunch of other stuff as well. A lot of GDB work now. And then we've got a half, maybe close to a dozen or so people now working on all sorts of various areas of the software stack, SDK stuff, Linux, QEMU, kind of the whole open source software stack. And the general idea is that RISC-Vi's a new ISA. We need kind of all software to run on it, which is it's a lot of work. That means embedded stuff as well as Linux stuff. So in Linux land, we have a lot of stuff working. The glibc port's been upstream for 6 or 8 months or so. We have, I know the Debian port has more packages building than the Itanium port does, so it's in reasonably good shape. And there's a Fedora version. You can go on the internet and get Fedora disk images. I use those to boot, and you can run native GCC on it, and it's a real computer. Right? We have a couple of hardware widgets available you can use where you can plug in graphics cards and run a browser, and it's kind of a real Linux-capable machine. The performance is on par with a ARM A53, or I guess one of the slower A53s, and it's kind of a reasonable thing you can use. And then in the embedded space, we have a lot of embedded customers. Sci-Fi has a lot of embedded cores, and we use pretty much the same tool chain and whatnot. And then we have some debug stuff like OpenOCD and embedded GDB target and those sort of things up and running. And then additionally, we're working on the embedded stuff you'd expect, like RTOSes and whatnot. Our Zephyr port's upstream, and then we have our RTEMS port that's upstream, and then there's a free RTOS port that's not upstream. So in general, in RISC-V land, software is in kind of reasonably good shape. The core of stuff is there, and upstream, the GNU stuff is pretty much all reasonably solid. But then the kind of edges of stuff is not supported. We don't have meaningful Java port. We have, they have some sort of interpreter based on libffi that you can get up and running in a couple of hours, and we have something like that. Similar for JavaScript, there's a port of whatever it is, Mozilla Central or whatever they call it now. That's again just like libffi based, no JITs or anything like that. And then we have a little bit of LLVM support that's kind of continuously getting improved, but it's not really in good shape yet. And then there's a ton of work to do. Things like improving code gen support, getting drivers in the Linux kernel. glibc is missing a bunch of stuff and has been kind of hairy for a while, so we're hoping to improve that. There's lots of work everywhere to do. So I don't know. I think these things are usually driven by, I suppose, what people have questions for and that sort of thing. So I guess we can just go around and ask questions and whatnot.
Let's just get a profile of the people in the room. So how many people here are actively working on RISC-V stuff?
Me. Yeah.
Okay. Yeah. So
good.
Okay.
So hopefully the rest of you will be by the end of it.
How many people here come from a sort of Linux application world, as opposed to embedded? How many people? Okay. Yeah. Linux application world. Yeah, 1 or 2. Embedded world. Yeah. Okay. About 50-50. Okay. And just for parts of the tool chain, GCC people. All right. Okay, that's clear. GDB people. Library people. Okay. What have I missed out? Binutils people. Okay. Jim, why do you want Jim? would you like to say a bit about GCC, because you're part of the GCC steering committee as well, and where we are with GCC for...
Well, I thought it was hard to do GCC work, but since Palmer is so busy he's never available to do any toolchain work, I've also had to work on a lot of other things. I'm also doing binutils and started doing some GDB work, and I help with nulib and glibc, and had to write a few Linux kernel patches
to
get GDB working.
Yeah, so Sci-Fi is still super small, so everyone kind of just does everything.
Whatever needs to be fixed.
Yeah, and everything's broken, so everything needs to get fixed.
Yeah, so Palm, you know.
I think there's no speakers. It's just for the recording.
You have to shout. The microphones are just for the speaker.
Okay. Okay, so I have to talk louder. I can do that. I'm American. I can talk louder. Right. So Palmer painted this pretty picture of how everything is upstream and working. From my point of view, it's a lot more complicated. The project was originally developed a bunch of GitHub trees, and some people still insist on using the GitHub trees, even though I'm trying to get them to use the upstream FSF trees. But binutils is fully upstream, and I'm doing development in the FSF tree and backporting to the GitHub trees. GCC is fully upstream, development in the FSF tree and backporting to the GitHub trees. We actually have 2 GDB ports, one in the GitHub tree and one in the FSF tree.
Yeah, though we're throwing away the GitHub one, hopefully now. So.
Yeah, hopefully someday soon.
Yeah.
And glibc, the 64-bit support is upstream, the 32-bit support is not. And there are some ABI issues that need to be resolved because a stat structure change. So the old 32-bit port that we have doesn't work with the current QEMU or Linux kernel. So that needs to be fixed.
There's some mushiness in Linux land. So basically in Linux land, people care more about the 64-bit side of things. So the 32-bit one is kind of just falling apart. But the Andes guys are going to eventually submit patches for the 32-bit glibc.
Okay.
I was hoping, we didn't get them in the last round, but hopefully we'll get them in eventually.
So when Palmer was talking about the Linux ports, Debian, Fedora, it's all 64-bit. There's no 32-bit support. There's no supported 32-bit Linux distro.
Okay. Nick.
It sounds like you've basically got everything working except maybe a few edge cases. Are you planning new optimizations or RISC-V specific enhancements?
Well, I would like to do some interesting GCC optimization work, but mostly I'm still trying to fix the things around the edges. I still have to finish my RISC-V Linux native GDB port. I have one more Linux kernel patch I need to clean up and submit upstream. And there's a whole bunch of GDB features I didn't even know existed that aren't working. So I'll probably have to look at a few of those.
Yeah, so we're hoping to have Jim look at like code gen quality in GCC, but as part of looking at it, he found an ABI bug in our like AUI PC, so like PC relative relaxations or relocations, such that the add-ins don't actually work correctly. So we've got to go fix it.
That's another problem.
Yeah,
yes.
which is that's going to be a big pile of work.
But I do find occasional time to work on an interesting GCC problem. Still trying to do a few small GCC issues along the way.
Are there anyone in the room got particular issues with RISC-V that we need to pick up? Ian?
The Go port isn't in.
No, there's no Go port, so it's clearly not there.
I thought so I'd seen some stuff go by about Go ports. I don't actually use it.
It does work with GCC, but it doesn't work with
Okay, so it's just the GCC or the GNU Go port or whatever it's called.
the GC.
Okay.
I think
There's a partial port that was done to an older version, but it was never submitted.
Okay.
I think that Stefan O'Rear
Yeah,
has a GNU Go port.
but not the other. I don't know what the other one's called. Is it just called Go, right? Yeah.
People call it the GC.
GC.
Oh.
Okay. Yeah. Sorry, I don't really use Go.
Okay.
Well,
Right.
we have GNU Ada because I did a GNU Ada port. The only time I've ever touched Ada. So.
Graham? Oh, Graham. Oh, yeah, right. Okay. We've got in the room, at least we've got Andrew, who's co-maintainer of the GDB world, Andrew Burgess. So, Andrew, did you want to comment on the embedded GDB world and what is there and what isn't there yet?
I'm not ready. It's all looking good. There's lots still to fix, but it's all right.
Okay. Yeah, let's go down this side. We'll start with Matthias.
So currently Linux distributions are starting to drop 32-bit ports or are thinking about that. Why do you start a new 32-bit port at this point? Why do you start a new 32-bit port for Linux at this point?
Well, so there's never been a 32-bit port that's upstream. So we don't have like a stable ABI in, say, glibc or like kernel land until there's an upstream 32-bit port of things. And a 32-bit port, the original 32-bit port, which is kept in sync with the 64-bit port, didn't make it upstream because the 32-bit Linux port was just broken. And we shelved it in order to get the 64-bit port upstream so we could let the distros start building. And then since then, the 32-bit port's been on the back burner. I think people in Linux land are less excited about 32-bit than 64-bit. In the embedded world, the extra cost of a 64-bit system can frequently be like appreciable in terms of the total system size. But once you have, say, like DDR or whatever, the 64-bit cost is a lot, less expensive. So the Debian and Fedora, in order to just reduce like the amount of work need to be done, they only build one ABI. So they only do like the hard float ABI with hard float hardware, for example, for all their packages and whatnot. Because in Linux land, that seems to be what people are more interested in. But yeah, the 32-bit thing is it does need to get done. And I think the Andes guys have 32-bit Linux hardware. So they're the ones pushing forward on that. But at Sci5, our Linux hardware is 64-bit. So it's hard to get a lot of time to work on it.
Alexandra, you had a question? And then...
I understand there are some issues with location view numbering for debug information compared with that had issues with relaxations. I would very much like to understand the issue so that I can try to find a way. Whom should I talk to? Ideally here. Is there anyone here who can talk to me about the relaxations and what may or may not happen so that I can try to figure out how to fit
specifically what do you want? So RISC-V is very relaxation heavy. So in the ISA, we basically have one addressing mode, which is like a 12-bit offset from a register, and that's for our loads and stores, and then the arithmetic operations work the same way. And there's two complementary addressing instructions. One of them is a 0 relative 20-bit offset, and one of them is a PC relative 20-bit offset. And that's basically all the ISA has. So as a result, all our code models are medium, so they're 2 gig or 32-bit offsets, right? 2 gigs on either side. And then we rely on relaxations, GP relative relaxations, that sort of stuff. We have a GP like MIPS does, but only one GP, not a GP per shared object.
And I'm right in saying relaxation is always linker relaxation.
Yeah.
It's not assembler relaxation, it's linker relaxation.
Yeah, it's almost entirely linker relaxation. The assembler does a little bit of stuff. We also have a compressed ISA subset, so like 16-bit instructions. The default ISA is 32-bit instructions, and the assembler can do some amount of converting to 16-bit instructions. But we do a lot of linker relaxation, for shortening offsets into 16-bit instructions and that sort of thing. And as a result of how our relocations are constructed, for the PC relative stuff, the load points to what's called AUI-PC, which is the PC relative addressing instruction, which adds the upper 20 bits of immediate to a PC, right? Kind of standard stuff, right? So we end up with basically just labels everywhere in the code because there's relocations everywhere and everything's split, and that kind of shakes out a bunch of issues. And I know Jim's run into bugs in our assembler where we're not properly splitting. So it's kind of just, we run into a lot of issues. Jim probably knows about specific issues more than I do.
Yeah, I haven't looked at this problem. I haven't looked at this issue specifically, but in general, we do have special relocations that we add to the dwarf debug info so that we can adjust things like line number addresses at link time, because code addresses change at link time.
Yes, yeah, that's another point.
So we have to update the dwarf debug info at link time.
Yeah, so basically we don't know the alignment of any instruction or the address of any instruction until it's been linked. So as a result, yeah, we have to do a whole bunch of relocations in dwarf stuff, and there's a couple of extra relocations for us, and it's you know, when I started, I guess I still don't really know what I'm doing, so I made a lot of mistakes, and as a result, there are long tail bugs kind of all over the place, and they can be very hard to find, particularly in something like this with the debug info and the line numbers, where like you'll only have an issue if, say, your function's large enough that you relax enough times that you actually end up with, you know, the debug info pointing to the wrong block of instructions, and it's hard to find, and it's only a little bit wrong, so you don't really notice it unless you're really looking. And when you're looking, the code's broken anyway, right? Because it's a debugger, so it's it's tough.
Even something as simple as getting function sizes right took a lot of work.
Yeah.
It was like 3 patches before I finally got it right.
Yeah, that was one of the first things Jim did. I remember, right? That was one of the first bugs you fixed was that
Yeah.
assembler. So.
I kept getting bug reports. The function sizes were wrong
Yeah.
in the ELF.
There's a question. Hold on, Jan. Can there's a question in the middle as well.
Oh, okay.
Back here. Okay. No, back here. I can't see. The guy there. Put your hand up. There. Oh no, that wasn't the person I was pointing to. But anyway.
You mentioned that the compressed instruction set is exploited in the linker, and I guess also the assembler to some degree.
Yeah.
Is there any plan to put awareness of that into the tool chain?
Yes, we would like to have compiler support for the compressed instructions, and probably be something similar to how the thumb2 support works in the ARM compiler.
That's what I was curious about.
Pardon?
I was curious if you would do a similar thing. Since
Yeah, we would like to do something like that. It's just a matter of finding time to do it. So many things to fix.
Yeah.
The code size, there's some code size measurements that various people have done. The ones we've done suggest that if you compare thumb against the current GCC and compressed instruction set, thumb's about 9% more compact across a fair range of embedded environments.
And do you plan to keep all 3 of them aware of the compression? And
So you at least need the linker aware of the compression.
at all times?
Some things can't. Yeah, because some things basically can't be compressed until relaxation time. So that needs to be aware of it. And having the assembler aware of the compression is pretty easy. So I think, at least, I don't know, Jim's doing it, but my plan would be to just add the cost model of compression into GCC and then allow the linker and assembler to transparently compress things.
Yeah, well, keeping the assembler support makes it easier for assembly language programmers.
Oh yeah, that's true, because then all the assembly code ends up compressed.
But yeah, new register classes for the compressed, the registers that you can use in compressed mode, and then instruction constraints to use the new register classes.
Yeah, so right now there's no feedback into GCC to tell you, like using the compressed register twice is better than using the non-compressed register once.
Yeah.
So our register allocation is a little bit on the arbitrary side for compressed stuff. So adding these in, and then I think at that point, once GCC knows about which ones to emit, once GCC knows about which ones are better to emit, you just let it emit that and let the assembler compress it, because we're not emitting, any actual bytes, because we have to, basically GCC never knows the address of anything because of all the aggressive linker relaxation we do. So doing the compressed stuff straight out of the compiler is, less exciting.
Yeah. Wait for a microphone.
RISC-V is not alone in that debug info gets out of date when you do linker relaxations and functions. Line numbers pointing to the wrong function when you look in GDB.
Yeah. What?
Well, if you can give us bug reports, if you can give us test cases and show us bug reports, we do have relocations for debug info. So in theory, it should be working, but yeah, it's possible it's not working as well as it should.
It's one of those things where the port's new and it hasn't been heavily used, so there are going to be bugs everywhere if you look, sufficiently aggressively. Yeah.
Sorry. Is the RISC-V ISA finalized now, or are there going to be extensions, changes?
So this is actually something kind of interesting about RISC-V. Okay, so RISC-V as an ISA, it's not managed in the same way that other ISAs are. So there's a standards body for it, and the standards body has the RISC-V ISA manual, which is currently a version, I think, like 2.2 or 2.3 or something like that. And that will continue to progress. And what happens is that whenever something goes into the standard, once it's been kind of ratified officially and all that sort of stuff, it's fixed, and then it has a name. So there are base ISA subsets, which are RV32I, RV64I for the 32, 64-bit ports. And once those are in, they're fixed forever. And they're fixed at version 2 of the base ISA, but then there are additional extensions that get added. So right now in the RISC-V ISA, there are like a half dozen or so extensions that are fixed. Right? So there's one for multiplication, one for atomics, some for floating point, and then the compressed extension. But then the ISA manual continues to move forward in version as new new extensions get added. Like we're working on a vector extension that's not finalized and will be finalized. There's a talk about that next. Or we just kind of fix either wording issues or mutual incompatibilities, or do something like there's a formal model working group for RISC-V that's going to have a formal model officially ratified, and then that will go in and that sort of thing. But the idea is that once an extension or base ISA or whatever is in, it's fixed forever. And so basically the core of stuff, so Debian and Fedora built to RV64GC, which is, so G is the general ISA subset, so it's multiplication and floating point and those sort of things. And then those will never change. So in theory, because Linux is ABI compatible, and then the ISA remains fixed, the software will continue to run forever, unless we find an ABI bug or something like that.
It's worth saying there are new releases which are mostly about clarifying ambiguities. Where it becomes clear. I mean, some of the stuff around different user modes, supervisor modes.
Yeah. And so, the instruction manual continues to progress, and there are basically bugs in the instruction manual that need to get fixed. So that happens in addition to adding new extensions and whatnot. But the intent is that things are compatible forever, unless there's a mutual incompatibility within the spec, which is a bug in the spec, and then that needs to get fixed, right? Because the spec at least needs to be self-consistent.
So how is this different from any other ISA?
So I think
Because that's how everything else works, right?
So that's not my understanding of it. Like if you look at like Intel ISAs, they tend to.
Yeah, so there's a difference in who decides what can get in, and the method stuff is decided what can go in and what not. But what users see is the same thing.
So I think there's two differences. So one of them is the extensions format, where you can basically pick which extensions you want, rather than having a rolling up version that contains kind of more every time.
Right.
And then the other is the commitment to not removing things once they're in.
No one does that.
Well, I know Intel has removed stuff.
Really?
Yeah. That was in shipping silicon. So it happens, and it's bad. So we will not, I don't own the RISC-V ISA. There's a standards body for it, but I will be very mad if anyone removes something from the ISA. And I think that's a general opinion of everyone in the process. So hopefully it won't happen.
Just to be clear, presumably you have some way of labeling the binaries to say it's using these extensions, so that you can then tell whether it's actually going to run on a real hardware that may not have those extensions?
Yeah, there's schemes. Right now the best scheme is for the ABI, and there's not much for the ISA part of things.
There's ELF things in there, aren't there?
There's some ELF header flags for the major extensions. And Andy's has been working on attribute support, like the ARM attributes stuff.
Yeah, that's always kind of. Right now, basically all the binaries that people care about lasting forever are GC right now, because there are no other extensions. So we kind of.
In the desktop Linux world, there's RV64 GC, and that's probably the only thing you'll ever see. But in the embedded world, everybody wants a different version of the chip.
Yeah.
So
the RISC-V ISA has a whole scheme for versioning extensions, and the base ISA is the whole thing. So the plan is to put that into every binary that gets produced. It's just there's a lot of complexity in making it all go together, and it keeps getting put in the back burner.
And for those who want entertainment, remember there's an 128-bit version of RISC-V, and ELF was never designed with the concept of having 128-bit architecture. So.
Yeah, so if you want to spend a lot of time on something.
That leads to the next key question, which is with all of these extensions and with vendors able to take the spec and do what they want with it, how do you manage the fragmentation that almost killed the ARM ecosystem?
So I think right now on the Linux side of things, which is where people are more worried about the cross-binary compatibility and whatnot, there we basically just standardized on RV64 GC, so it's not really fragmented. And then in the embedded world, the ISA alone is not generally enough to be portable to various things, right? There's all sorts of platform issues and whatnot. So there, it's up to the platform vendor to make sure that you kind of
And is there any regulation at the platform level for like device drivers and?
So there is supposed to be a RISC-V platform working group, which I think I'm supposed to be running. But I've been saying that for a year or so, and it hasn't happened yet. So eventually it will. We have a talk at Linux Plumbers that is called the RISC-V Platform Working Group that I'm giving. So I'm at least on the hook for something like November. But yeah, no, it's an important thing to do. It's just there's too much work to do, and it kind of keeps getting put in the back burner. But at some point it will be an issue. I think more on the platform side of things than the ISA side of things. There's a lot of detection mechanisms in the ISA, and all of the choices of extensions are not smart ones. So I think people are kind of, if you have a floating point unit, you can probably afford a multiplier, that sort of thing. So it's not like the total product of extensions is going to actually be out there. But I think that the idea behind the platform spec is to provide profiles and driver and that sort of stuff. Just not done yet.
Well, we do have one problem in the Linux world, which is the Shakti IAT Madras. There are RV64G. They don't have the compressed instruction support. And that was a communication problem. But otherwise, everybody else in the Linux world is RV64GC.
Yeah. It's also an issue for some like hobbyist or core sort of things, where doing the compressed instruction set fast is a little tricky. But the binaries are all 64 GC, so people will run it.
Other issues, limitations, bugs people have found. Questions? Yes, Nick.
So this is more for you, Jeremy. How does the RISC-V pan out in terms of power distribution? And you've given us talks before about how you can glean information from cores by measuring power and heat and so forth. So how's RISC-V work for that?
So, oh no, I've got a microphone on. We did some early work looking at RISC-V, and the Berkeley guys did a lot of work on the early things. And certainly one of the most exciting things from RISC-V was the very early rocket chips came out with an astonishing energy profile that made them far, far more efficient than ARM processors. I'm always a bit nervous when I see university experimental processors report such figures and how it comes when the rubber runs the road. We haven't yet turned our machine learning stuff onto actually measuring. We have actually got some kit we can measure, but because a lot of the embedded stuff is done on FPGAs, if you want to save energy, you generally don't put it on an FPGA. But Graham, have you started looking at that yet? Or where's Craig? Have you done any work with the RISC-V energy measurement yet, Craig? No. So the answer is it is to be done. The initial research suggested this was potentially optimal. The observation is that there's a close correlation between speed and energy. You can do all of machine learning, but actually the best thing is just run it fast and turn it off. So the indications are that RISC-V should come out with a reasonable energy profile.
Yeah,
well, there's a lot of companies making RISC-V chips, so it's not necessarily true generalizations from one company's core to another's may not hold.
No, I mean, but from an architectural point of view, we haven't seen anything in the architecture that says, oh, this is the sort of architecture that always does dreadfully on energy efficiency measurements. There are some manufacturers whose chips are famously good at burning electricity and others that are less famous for that. So from architecture, yeah, if you don't build it with a low power process, it's going to use more energy. But architecturally, it's a compact instruction set. It's a sensibly organized instruction set. It doesn't do things that you expect to burn power. So all the preliminary stuff is it's good. At some stage, we will turn our energy measurement guns on it and actually get a hard figure. We haven't got around to doing it yet.
Yeah, it's like Jeremy was saying, the the implementation's like the first order constraint in energy stuff, not the ISA. But if you look at the implementations of RISC-V chips to get, say, like similar frequencies to an ARM chip, we tend to lose a cycle in the front end because ISA is a little simpler and sort of, registers are lined up and that sort of thing. So you may or may not be able to have a one cycle shorter front end, which then buys you a bunch of energy and whatnot because your branch predictors are smaller and your latencies are lower and all that sort of stuff. But fundamentally at the ISA level, it's kind of all a little bit mushy in terms of who's better or worse. As long as you don't do something crazy, then it's not a big deal.
More questions? More comments? Yes.
I assume that you're not having any libstd C++ problems that I can help with or need to be aware of. I've not seen any issues with libstd C++ affecting RISC-V, so...
Yeah, I don't think I've run into anything. I don't know.
No, there's not really any target-dependent stuff.
Yeah,
in
that's what I
C++.
figured, yeah. Great. Okay.
Yeah. I guess that's good. Yeah.
One thing I would just add on, though all the bits of the tool chain are there are areas of work. And one of the areas, when we did the size measurement, at first, RISC-V at one stage looked absolutely terrible. And it was when we realized that though this is an embedded benchmark suite, it still uses floating point. And this particular customer we were evaluating for explicitly did not have a floating point unit. And the ARM floating point emulations are really tightly coded pieces of assembler. And the RISC-V floating point emulation is just the standard compile it in C. How many people want to use floating point in an embedded world but not put in a floating point unit? If you want to do a load of floating point embedded, you put a floating point unit in. So I suspect it's one of those things, yes, it would be good to do, but it probably doesn't matter to many people. If you're emulating floating point, you probably don't care anyway. And there's those sort of corner cases which more work would help.
Well, there's a big difference between your embedded floating point emulation, between it being 10 times slower or 1,000 times slower than real hardware.
So I haven't looked.
Difference.
Yeah, I agree. So I haven't looked at. I've concentrated just because of the particular customer who's driving this work. I've concentrated on code size because they were trying to make a very small chip, which is why they didn't want a floating point unit on, but they wanted to address. It's all very well saving processor chip space. If you then go and blow up your memory space, there's a crossover at some point. So from a floating point of view, the libraries were a few times bigger, but it is a few times, not a few percent bigger. But I come down to the thing is, if you really care that much about floating point, put a floating point unit in. Any more comments, questions? Yeah.
I've been asked to ask this question. Do you have any forecast when the new Linux kernel will boot on the hardware Hi5 Unleashed? It doesn't boot, unfortunately.
So it depends on what you mean by boot, right?
It doesn't work compared to the kernel that actually works.
Yeah. So 4.18 just came out. So the 4.19 merge window is closed in the last couple of weeks, and during the 4.19 merge window, we got in the drivers for our interrupt controllers and timers and that sort of stuff. So 4.19 will be able to boot. I mean, 4.18 could boot, right? But there was no interrupt controller and no timer, so you couldn't do a whole lot, right? So 4.19 boots, right, and has a serial terminal and an MFS and can take interrupts and timers and run the vast majority of user space code. But it does not have drivers for, say, the PCI Express stuff or the SPI or SD card or any of those sort of things. So those are kind of the next round of drivers to do, right? So the core Arch stuff has been in for a while, but that's not very useful without some way to talk to things. And then in the last 2 releases, we've gotten kind of the core set of drivers in, right? Interrupt controllers, the simple serial terminal, and the timer stuff. And then it boots, but it's not super useful, right? And then now we're working on getting the rest of the drivers in, which will take another couple of release cycles. But hopefully, 6-9 months or something, and we'll have the vast majority of drivers in. Right. Of course, then there'll also be more things to write drivers for. So it's an ongoing process.
Okay.
Yeah, sorry, hopefully that was good enough.
Okay, any more comments or questions? As you can tell, there's there's 1 or 2 of us working on RISC-V here this weekend. So we'll draw things to a close on the general RISC-V BoF. There is a BoF coming up at 2 o'clock on the vector extensions. So RISC-V has a pretty sophisticated idea for runtime configurable vectorization. There is a BoF to discuss that and some of the challenges to the compiler world of implementing it. And Graham and Roger Espasa will be leading that, and Roger is on his way from the airport. Oh no, he's arrived. He's arrived. Okay, so we will start about 2 o'clock to give everyone a chance to come and join in. So thank you very much.